Hello, professors. My presentation is about the case the IOSI merge alloys, especially A356 and IOSI 7 merge. I focus on how casting defects and the T6 height treatment interact. The main point is simple. T6 can improve the matrix strength, but reliability is still controlled by the defect forms during the casting. So I will explain this as one manufacturing chain from casting to failure behavior. The background problem is very practical. These alloys are used in lightweight transport components, but because they cast well and can be edge hardened. However, their properties are not always stable. Casting can leave porous shrinkage cavities and offset films. T6 treatment can raise strength and hardness, but it cannot erase those defects. Therefore, the important question is whether the complete manufacturing route gives consistent reliability, not only good average strength. The material system starts with the aluminum matrix. It has an FCC structure, so it has good ductility, but it needs stringing for structural use. Silicon improves the castability and forms the eutectic structure. Magnesium enables the precipitation handling during the aging. Iron and magnesium are important when the recycling metal is used. Because iron-rich phases can reduce the ductility, this means the alloy design, microstructure, and the processing route must be considered together. This framework organizes the report, the casting route, and metal handling affect filling. The filling and solidification create the degrant scale, segregation, and defects. The T6 then modifies the matrix through the solution treatment, clinching, and aging. The final performance depends on the most strength matrix and the most severe defect. This framework prevents the presentation from the treating casting, handling treatment, and fatigue as the unrelated topics. The main defects can be grouped into four types. Gas porosity is linked to hydrogen rejection during the solidification. Shrinkage porosity is linked to fading, shortage, and hot spots. These forms come from the turbulent falling of the outside surface, so they behave more like the thin cracks than the simple pores. The macro segregation and intermetallic phases can reject funding and create brittle regions. For design, the critical defect matters more than the average porosity. This slide shows why the defect characterization matters. A polished 2D section may show porous, but it does not always capture the true maximum size, conductivity, or position of the defect. Also, so the X3 macro CT gives the dimensional information, which is more useful for fatigue assessment. The limitation is practical. The CT has caused resolution and scanned volume limits. So in industry, it should support, not replace, process monitoring and statistical inspection. The T6 have three main stages. A solution treatment dissolves soluble physics and modifies eutectic leaking. Quenching remains a superstructured solid solution. Artificial aging forms one might assign precipitates, which increases the resistance to dislocation of motion. This explains the improvements in strength and hardness, but the porous and oxide forms are not removed by T6. Some gas-filled the defects may even enlarge during solution treatment, so testing quality remains essential. The SEM evidence shows that the head treatment changes the microstructure. The T6 have fragment and sulfuric gas. The eutectic stick, and aging from the mesh precipitates in the aluminum matrix. This precipitates handle dislocation motion, so the strength and the hardness increase. However, the stringing is not the same as the reliability. If a large pori or beforms remains, failure may still start there. So, microstructure improvements must be interpreted together with the defection condition. Mechanical performance should include the strength, ductility, and fatigue. T6 have increased the strength, but fatigue often starts from the defects at the stress level below the monotonic yield strength. The ROI and curves shows that the defect size changes the endurance limit in A3, 4, 6, and T6. Setting and curves extend this idea to for scale wheels using the defect statistics and local stress analysis. This is why components reliability cannot be just judged from average tensile strain alone. The recent efforts aims to link the data processing with the internal equality. That's where CT provides the 3D defined data. Machine learning classified the die casting condition related to the porosity, and the simulation optimize the thermal and solidification conditions. The recycled alloy design reduces primary mental demand, but raises the chemistry and the effects control needs. These tools are valuable, but require metrological validation. As the model alone is insufficient without the understanding the effect mechanisms. The critical synthesis is that no single step should be optimized alone. A faster filling may improve the productivity, but increase the oxide entitlement. Longer solution treatment may improve the silicon morphology, but increases the pori growth risk. More recycled material improves the sustainability but can increase the impurity reliability. So therefore, the best decision is integrated the chain, the melt, quality, filling, solidification, T6, inspection, and the defect sensitive design. To conclude the case, the IOSM alloy gained the performance from the full manufacturing sequence. Testing defects to create the mine reliability risk. T6 improves the matrix for the silicon modification and the wedge design precipitation, but it cannot remove porous or bifilms. Emphatic performance depends on the critical defect and stress volume. Therefore, the reliable components requires the integrated control of the multiple handling, filling, solidification, T6 treatment, inspection, and defect tolerant design. So thank you, professors.